Okay, let me get started then. So I'm going to begin just by, as I said, a little bit of introduction to me, to the project and what we're doing. My aim is to talk for about 40 to 45 minutes to give time for questions at the end, and also just very aware that it's people's lunch break and they might want to see some, well, I'd like to say sunshine, but perhaps better description would be clouds and wind, looking at what it's like in Southampton. So once again, thank you for giving up your lunch break to come and listen. My name's Christine, and I'm a professor of OR at Southampton in mathematical sciences. And I've worked on a diverse array of projects. I think that's one of the things that keeps me interested, is looking at lots of different applications for about the past 20 years. The two projects I'm going to talk about today are very close to my heart. Their aim is to allow the same flexibility in private mobility as we have now, but with a decreased ownership of cars. So this is what we're looking at. So with that big kind of looming climate change agenda very much in there, but also in terms of maximizing the efficiency of our resources as well. The work is being funded by EPSRC. The funding for both projects hasn't actually quite started yet, but we have the awards. So I put the grant numbers here. And what that means is over the next year or three, you should see some more developments in some of this work as it comes through. Let me go to the next slide, if it's going to let me. Okay. Just some motivation then for what I'm going to be talking about today. Data shows, and this data comes from the Brookings Institute, which is a policy think tank based in Washington, that private vehicles go unused for about 95% of their lifetime, which is, as you can imagine, a complete waste of resources. So we're building a lot of these cars and for them to sit on our driveways or in car parks, etc. There are different ways of solving this problem. And the reason there is a problem is because we're looking at a world which has got finite resources. So how do we solve that problem, but still maintain that quality of life that we have today? There's a few different ideas out there. Car clubs and short-term rentals are one of them. And those are what I will talk about for the main part of this presentation, as you'll see when I get to the agenda. And these allow people to be able to access a car fairly short term, so they don't have to book necessarily a long while in advance, can have the car and use the car for a fairly short period of time, and pick up and return that car fairly close to where they are. So the aim of these car clubs, these short-term rentals, this car sharing, is that people can access a car when they need to, but they don't have it sat on their driveway for most of the time. And Zipcar is a very good example of this and has got quite prevalent particularly in London. You will see quite a lot of Zipcars. They are also, I did write this down, available in Bristol, Cambridge and Oxford. So there's my plug for Zipcar, but haven't made it to Southampton yet, I would say. And this graphic at the bottom comes from their website, just to say how you would do it. Zipcar is a subscription. You would join Zipcar, you would then search and book for the car that you wanted, and you would end your trip. And this is one thing which makes it a little bit different from car hire, is that with car share, you can often end your trip somewhere different from when you started. And I'll talk a little bit about more about that as we go through. Now, another option for reducing the use of private cars is to use something which is called, and now relatively well known as, demand responsive transport, or DRT. What's been acknowledged as being very difficult within the transport network is that last mile transport. And many of you who've worked in OR, and particularly in logistics, will know last mile delivery is a key problem at the moment. So how you deliver your Amazon parcels to your doorstep, for example. But that's similar in transporting people, how you get from the railway station or the bus stop to your house, particularly if you're in a rural location, isn't actually quite an expensive and difficult problem to solve. Demand responsive transport goes some way towards that. So you will have a group of people sharing a car or a minibus. There's some ways like ride sharing, and its route depends on demand. I was joking with my children the other day as we drove to band practice and picked up children from 2 different households on the way there and then dropped them off on the way back afterwards, that many people do this kind of demand responsive transport informally already. But how about when you're in maybe a different city, or you don't know people, or so on? How can we do this in a more formal way, with payment in that case changing hands? And there are various companies that do this. Uber has a prototype which is in the US, and I've put Lyft Tango and Padam Mobility in there as companies that do build software for similar things. In the UK, Dial-A-Ride is the most obvious example of this kind of transport solution, which has typically been for people who are elderly or have reduced mobility. And so we're looking to build on that and build it out to a bigger community. And that's the kind of question that we have. So can we use operational research and optimal pricing in particular, which I'm going to talk a little bit more about pricing in this talk, to help these services become self-sustaining? So to get them self-sustaining, they need to be attractive to the people who will be using them. They also need to be affordable for the people who are using them. But equally, there's something on the other side as well in terms of the organizations that are running them. Can we make it so that they are not running at a loss, for example? Or if they are running at a loss, we can understand what that loss is, and we can use public subsidies to maybe bolster it because of the benefits that we see elsewhere. So these are some of the questions that we'll be considering later in this project. Let me go through the agenda and I'll talk about what I'm going to say today. What I'm going to talk about today then is, I've split it into 4 different aspects. The first part I'll talk about is car share models. I'm going to go into some queuing theory and some Markov chains. There will be some equations in this bit, but if you've done queuing theory on a master's course or an undergraduate course, or even later as part of your training, you will, I would hope, understand what I'm talking about. So the models we start with quite simple, and then we build in the complexities. So those be the car share models. That car share project is joint work with Professor Rim Mahala, who's at King's College London, and also Professor Beatriz Oliveira, who works in Portugal, University of Porto. And we'll go through some preliminary results as well for that car share project. I will spend a lot less time talking about the demand responsive transport project. This is a project, we've called it Adroit. Again, joint work with Rim at King's College, but also Julia Bennell at Leeds and Chiara Calastri, who's also at Leeds. And that's a big 3-year project, which is formally starting in November. So there's stuff happening on it, but there's less that I can actually report on now. What I'll talk about is what are the key modelling questions. How do we think this is going to pan out at that point? And then I'll conclude and talk a little bit about future work at that point. I'm just going to check if there's anything in the chat. Wiggly bus. Thank you, Jen. I can see one comment in the chat before I move on. The Wiggly bus in Pewsey Vale, Wiltshire in the late 90s. Yes, this is just the kind of thing that we're looking at and seeing if we can make it work. But yeah, I love the name. That is very good. And I suspect it has some indication of what the routes would look like. Okay, so we'll go through to the car share part of it and the car clubs, etc. How are these different from car hire? This is the first obvious question, because there's been work in the literature. Dong Li, for example, who's now at Lancaster, has done some very interesting work on pricing of car rental, for example, and there's other work out there as well. How what's on offer now different from those car rental models, and why do we need something different, I guess? One thing that's different is the duration of hire. Typically, the car is used for a shorter period of time. It might be hours rather than days. That does raise some challenges. So as you see in the sign here, this is the Enterprise Car Club, which does self-service vehicle rental. Cleaning the car, checking the car, etc., is all requires some kind of various operational changes to doing that. And here you just park your car and someone else will then come and pick it up when it's their turn to hire it. But that duration of hire is quite a key one. People aren't going to have this for their whole 2 weeks of their holiday, for example. Planning ahead is also different. In traditional car hire, bookings would arrive a long way in advance. If I'm booking a car for my holiday, it would be maybe a few months in advance that I would remember to get round to making that booking. Whereas with car clubs or this car share, your bookings are arriving much closer to the time, which means there's less kind of need for this almost time-dependent pricing than there would be in your traditional car rental. And also less time for doing planning, for example, moving cars around and changing the fleet size. So sometimes that is possible in car rental. The other thing that I alluded to a bit earlier was these one-way hires. So one-way hires mean you pick up the car in one location, you drop it off in another location. And we saw with the Zip car that they have something, I think, called a flexi journey where you would do just that. So it might be you walk to the supermarket, you pick up the car at the supermarket, you drive your shopping home and you want to leave it somewhere near your house, for example. These one-way hires, we're not going to consider kind of different pricing for one-way hires in what we talk about today. That's definitely in the very much needed future work. But what problems that cause and what issues that cause is that your cars will often end up in the wrong place and not where you need them. And if you think about the bike shares or the scooter shares that you see around cities nowadays, you will sometimes see, in the morning that everyone will take them from the suburbs into the centre of town. In the evening, they might be going back again, but in the middle of the day, people will be moving these bikes and scooters around and they won't necessarily all be where they need to be for people to pick them up. With cars, it's one step harder in that you can't put your cars in the back of a van and transport them to the other end of the city. Being an academic, I'm going to give you some literature. So this is what other people have done. I'm not going to dwell much on this slide, simply to say these problems are being looked at quite a lot from Europe and a couple from Singapore, if you look at the locations of the applications that you see in here. Simulation is one of the key ways of looking at this because it gets you that chance to include all those complexities and model accordingly. Straight optimization, such as a mixed integer linear program, is also used. So this is where you're kind of bringing down all it to its slightly simpler forms and possibly taking account in different ways of the uncertainty in arrivals, etc. And so there's various different ways that people have looked at this problem. Let's look then at how we're going to do it. So I'll talk a little bit about the problem that we are solving and how it fits together and what modeling choices, I guess, we've made along the way. We've tried, when we started looking at this problem, to start with the bare bones of the problem, if you like. Let's think, what's the simplest way we can describe this situation and put some maths behind it and see if we can come out with some general results. With that in mind, we've assumed all the cars are identical. We're just going to say there's n of them. And customers hire them with a probability dependent on the price for 1 hour's hire. Now, we're looking at pricing, so it's important, even though we're looking at the simplest model, that we've got some price dependence in there so we can see how prices affect things. Modeling the price dependence or the probability of someone accepting a hire, we use a concept which is called reserve prices. Now, if you've studied economics, this will probably be familiar to you or anything in revenue management. But a reserve price is basically the price you have in your head that you think that in this case, the car hire is worth. So this is the most that you would be prepared to pay for something. In this case, the maximum amount that a customer is prepared to pay for a 1 hour car hire. They may have it for longer than an hour, but that's the maximum rate they would accept. And you will typically see within a market that there'll be a distribution of reserve prices for each product. So if you asked people what's the most they would pay for car hire, you would probably get a few different numbers coming out if you asked kind of a classroom full of people. Of course, the problem is that when people arrive to book that car hire, they're not going to tell you what their reserve price is. They're not going to type that into their phones or into their computers when they're booking that car. So you have to take account of the fact that you've got this distribution of these reserve prices. So the probability that a person drawn randomly from the population will pay a price R is equal to the probability that their reserve price is greater than or equal to R. So R we're going to use as our fare, and our letter that means the fare. And this is also what you call their willingness to pay. Now, there's a few different kind of typical distributions that people will use for reserve prices. The most obvious one is we don't really know, so let's assume they can have any reserve price between 0 and some maximum amount. So that's the uniform. And what you see is when you are charging, say, a price 0.8, then the probability that someone will accept that price is going to be lower. So here it's about 0.2 than if you were charging a price 0.4, for example. So where the probability of them accepting that would be 0.6. So you've got this kind of straight line in your willingness to pay graph. And this is almost the simplest you can go with in terms of price dependence, kind of linear price dependence in the probability of purchase. So it's a good one to start with to get some general results. Now, the other one we've considered, I'm not going to show results with this today, but the other one we've considered is what's called a logic price response function, where we have something probably a little bit more realistic. So if you look at people's reserve prices, then they will be around some kind of popular value. And this is generally the case for goods where there's a obvious market price for those goods. For example, you might be selling Coca-Cola, and people who drink Coca-Cola quite regularly will know roughly what the price of that Coca-Cola should be within a particular shop, and will have a reserve price that's somewhere around that. So you kind of have this market price. And the willingness to pay for that shows a more respectable curve. Straight line always looks like it's the simplest model you've thought of. This shows a more respectable kind of reverse S-shaped curve for the willingness to pay and the probability of purchase. The other assumption that we make here is that we've got an infinite population of potential customers. Now, we don't truly believe that the population of potential customers is infinite. What we really mean by that is if someone comes along and decides not to purchase that product, it's not going to affect how many people come along in the next time period. So that's don't have to get to a huge customer population before that assumption is reasonably accurate. Then what do we assume about arrival? So again, if you've done queuing theory, you'll recognize I've got a lambda here. I'm talking about arrivals. So it always seems to be lambda when we're talking about queues and arrivals. Customers arrive into the system looking to hire a car at a rate lambda, which we're assuming is constant across the day. In reality, that will vary across the day, but in terms of getting some general results out, we don't need to worry too much about the time dependence. I'll talk a little bit about that later. And then a customer is going to actually say, yes, I want to hire that car with a probability that depends on the price for the hours hire. And we've got a function omega r here, which describes that probability. And that's what we saw in the previous two slides. So it's either that reverse S-shaped graph or it's your decreasing linear slope. This is purely notation. We're going to call that lambda of r, which is lambda times omega of r. And so we've now got an arrival rate that depends on price. Arguably, your service rate would depend on price. You could say, if I'm paying more, I might be quicker to get my car back. but we've ignored that for the moment, and just assumed that the service is constant. So there's no price dependence there. Someone is doing that journey, they're not going to do a shorter journey as a result of paying a little bit more. Now, whether that is needed or not, that's something to consider next. But certainly at the moment, we're assuming that they will return their car at a constant rate. So on average, they'll have that car for 1/μ time periods. This is where the pricing comes in. So the pricing scenarios, we have a fixed price, which is simple. It's easy to implement, this queuing theory. A price that depends on the number of cars on hire, which is more complex, but potentially more lucrative. And we'll show some results that show it does improve your revenues. And we consider two options in that case. So either a different price for each number of cars on hire. So if you had 100 cars in your fleet, you would have 100 different prices. Or alternatively, a probably more practical approach, which is to say I'm going to have two prices, one when I'm at a low utilization and one when I'm at a high utilization. And we'll show results with both of those. Time-dependent pricing, I'm not going to say much more about in this presentation. Essentially, what you're doing is saying my arrival rate into that system is going to be different at different times. And so if it's busy, I'm going to charge more. If it's empty, I'm going to charge less. And we can use the queuing theory results or the other results we've got here to decide what those optimal prices should be. Ran out of space in the presentation, so no results from that, but I can talk about it later if anyone has any questions. Now, essentially here, what we're trying to do is maximize the revenue that comes through, which is one slide away, but I just wanted to say a little bit about that. So our aim in this point is to maximize the revenue. Now, there are some discussions afoot, and Arnie Strauss, who's now based in Germany, is a good person to look at on some of this work in terms of, is expected revenue always the best thing to optimize? Because in some ways, what you want is you want to move the prices around so that you are pushing people to use the service that you want, probably not so relevant in this particular case, more for the demand responsive transport, but equally you don't want to be charging over the odds. Depends in this case whether it's a private company or a public service that you're optimizing here. But for the moment, we're going to be optimizing expected revenue. Right, now starts the queuing theory lecture. No, I'm not going to go through lots of queuing theory, but for those of you who've seen it, you may recognize these nice transition diagrams that are very useful for understanding what your system is doing. So in this case, what we have is an N server queue with no waiting space, where the state is the number of cars on hire. If we start at this end, where we have a 0 here, that means there's no cars on hire. Someone will arrive at a rate lambda and they'll purchase with a rate omega of R. And so their overall arrival, if you like, to hire a car is this lambda of R. So they will hire a car, we'll get one car on hire. So as we move along this chain, we get up to the point where we have N cars on hire. Going back down the chain, you can see if we've got one car on hire, we'll return at a rate mu. If we have two cars on hire, then we're looking for the one that returns first. And if we're looking at the rate of the first thing to return, first thing to finish its service, it's a bit of a complicated way of saying it, and there's two processes going on, then the rate will be 2 mu. And similarly here, 3 mu and up to N mu. So this is, as I say, like an N server queue where the cars are the servers. We don't allow people to wait if there's no car available. We assume they disappear and go somewhere else. So what we're interested in is the steady state revenue. The steady state revenue, I've written it as an expectation of capital R, of R, which is our revenue, is the amount that someone will pay for an hour of hire, multiplied through by the expected number of cars that are on hire at any one time. So this will be if we're in state I cars are on hire. The probability we're in that state is pi I, that's what we've written it as. And so the expected revenue is R times the sum of the I pi i's, which is an interesting phrase to say. Okay, so R I pi I gives us the expected steady state revenue. So this does assume that we've reached a steady state. Any fluctuations have gone. Now, we do know how to solve this. This is why it's always nice to start with queuing theory, because you've got a lovely way of getting to some equations. They don't look that pleasant, but they are nice-ish, and we can calculate them quite quickly, which is the main thing with these, unlike running, say, a computer simulation, which might take a bit of time. And if we put those all together, this is probably the worst of the equations. We get an expected steady state revenue that looks like this. So don't look too much at the details. I'm not going to go into what the details are. But what I would say is it's got that R dependence in there, and we can optimize now for different expressions for omega of R, which fits into the lambda of R, which fits into the rho of R. So we've got the omega of R in there, that willingness to pay distribution, and different values for N as well. We have shown this is concave, so it's got a nice single peak, effectively, is what we were looking for, which means it's actually not too hard an optimization to solve, so it's relatively quick to optimize. Assuming omega of R follows some fairly easy conditions, and the standard willingness to pay distributions fit those conditions. So we have a nice optimization here. And this is looking at our first model. Now, what we thought, and based on, I guess, a lot of my background in revenue management, is actually, wouldn't it be nice if we had some kind of dynamic pricing? Now, typically the dynamic pricing you might be using a dynamic programming or something else to solve this problem. In this case, we thought, well, can we do this by just making our queuing model a little bit more complicated, and think about what's the optimal price to charge when I'm in a particular state? So how about I change the price when I've got a different number of cars on hire? This case is for 2 cars. So it's a very simple example. Very small fleet, N equals 2 cars. When 0 cars are on hire, I'll charge a price R0. When 1 car is on hire, I'll charge a price R1. Now, we'd hoped, that we'd be able to use queuing theory and get some nice analytic equations for that. Actually, that doesn't work quite so well here. It's a little bit more complex than that. We need a more complicated Markov chain to describe it. Our state now becomes how many people are paying price R0, how many people are paying price R1. The reason we need to take account of that is when we calculate the revenue and the expected revenue. Because if people are paying different prices, we need to know, in that state where 2 people are have a car on hire, so one of these 2, are they both paying the high price? Is one paying the low price and one paying the high price, for example? So in order to calculate the revenue, we need to keep track of that, hence the kind of slightly more complicated state space. And also how we draw those transition diagrams and kind of translate those into rate matrices. We have to think a bit about what transitions are allowed, and so what states are allowed as well. For example, if you look at, in this case with N equals 2, we have a state where we have 1 car paying the low price and 1 paying the high price, and a state where 2 pay the high price. We don't have a state where 2 are paying the low price, because that isn't feasible in the model that we've set up. And so thinking about that state space and thinking about how we can generate that automatically for high values of N is also one of the challenges that we've had on this project. I've included the expected revenue equation in full for this, this example where N equals 2, just so you can see what's going on. So you can see here we're paying R0. In this case, we've got in the state 1, 0, which means 1 person is paying the low price, 1, 0 are paying the high price. This is our probability of being in this state, this pi 1, 0. So we're calculating the expected revenue. We will be the revenue generated from being in that state times the probability of being in it. If we work it all out, we get some fairly nasty expression there. And in general, we can write down an expression for that, as we see below, which we can put into code. What we do see is that as n increases, the complexity also increases. This is n equals 3, and you can already see that the number of transitions is quite big, the number of states is quite high. But what we see partly from experiments, but also just thinking about the problem, is that if you're in a situation where you've got quite a busy system, so what we call the traffic intensity is quite high, you won't actually spend very much time at all in this state where nothing's on hire, or one of these states where there's only one car on hire. You'll spend a lot of your time kind of flitting between these top two layers, which means that full state dependent pricing has marginal benefits. So what you're better off doing in those cases, partly from a practical perspective, because in practice, a customer would get very annoyed if the price was changing, constantly as we move. One car comes back, 5 minutes later, another one comes in. You've got to see one price 1 minute, 5 minutes later, another price. Then having just two prices out there may be the way to go. And so we look at the case, sorry, just checking those questions. So we can look at a case where we have two different prices on offer. So Sheba's asked why different prices. The reason we're charging different prices is we think that if you're in a system or in a state where not many cars are on hire, you want to encourage people into that system. And so you might be charging a lower price. Whereas in a state where you've only got one car left, for example, then actually you can be happy to hold out for a higher price and maybe take a little bit longer to find somebody to take on that extra car, but it gives you that extra bit of revenue. So this is a fairly standard kind of revenue management strategy that you would see on the airlines, for example. If they are filling up quickly, then they will increase the price. So that's the basis for this model. Okay, we have then a low utilization price, we have a high utilization price, and we can see now how that changes the number of states that we have within the model, and the number of states gives an idea of the complexity and the difficulty in terms of modeling and optimization. I've just included up to n equals 5, but you can see already that with full state dependent pricing, so this would be 5 different prices, the number of states we need is 126 in this case, whereas we only need 20 if we look at 2 prices. So it definitely simplifies the modeling, but also practically, I'd argue, it makes things a little bit easier. And we'll see when we look at the results how it affects the expected revenue. Looking then at the 3 prices, I've shown you that very complicated diagram a few slides ago. This is it with just 2 prices, and you can see that it's still complex. There's still quite a lot of stuff going on here, but we've reduced the number of states from 9 to 14. We've got slightly different transitions coming through there, and so we've got a simpler problem and an easier problem to solve. That's the modeling that we've done so far. I'm going to present a few results now, which I've picked. I've not got many results because I'm not really wanting to show you lots of the numbers, for example. The results I'm aiming to show you are to show you kind of general ideas and things that we've found when analysing this problem. So we'll look at some for constant price and we'll look at some for state dependent price and see how they vary with how busy the system is, for example, and also how those different models affect things. A few assumptions that we put in was when developing these results were reserve prices are distributed uniformly between 0 and 1. As I said, we have run results for logistic, we're not included them here. Arrival and service processes are both Markov, so we've got Poisson arrivals, exponential service times, which is a good first approximation, but acknowledging that That's probably not 100% accurate in practice, and that the system is in steady state. Okay. So this is the first set of results, which comes from the fixed price. So we're saying everyone pays the same price for the cars, regardless of how many are on hire. What's interesting here is if you start with lambda equals 1 and lambda equals 10 here, which are the bottom two curves on this plot, you've got a situation where the system's not particularly busy. So there's not that many constraints in terms of cars. What you see here then is that the optimal price to charge is around 0.5. Now, if you were looking at a fully unconstrained system, so if you've done any optimal pricing in economics, for example, the optimal price to charge, if you've got a uniform willingness to pay and uniform reserve price distribution, is halfway through the interval. And so we see that here, these results come out. So effectively, when the arrival rate's low, we've got an uncapacitated system and we're getting the results we would expect, which is a good check that everything is sensible. When we move to higher values of lambda, so the system's getting busier, the curves become more skewed towards the right. So our peak is heading upwards, and our optimal price to charge is heading to higher values, which is, again, what we would expect. If there's a lot of demand on this system, then we can afford to charge a little bit more because we know there's going to be lots of people coming along to buy things. This graph is just looking at the case where n equals 4, so very small fleet size, but just to give a general view on an example that's easy to kind of understand and follow of what's going on. We can see on the lines correspond to different prices that are on offer. So this is for the full state dependent case. We charge R0, which is less than R1, which is less than R2, which is less than R3. So we can see that we've got that right ordering of the prices that we would expect. What you can also see is that the price we'd charge for a constant, if we were only charging one price, this grey line, falls somewhere between that kind of upper and lower price. So again, it's doing something sensible. The price is increasing as the system gets busier, which is we move left to right. And we will get a higher price for when we've got 3 cars on hire and looking for that fourth than we would when we've got no cars on hire and looking for our first. So it's doing things in the right direction. Now this one is a very recent graph. We've only produced it this week, so this is definitely hot off the press, which is looking at the percentage improvement in expected revenue, again with n equals 4, so with our fleet size of 4. What you're seeing is actually relatively small improvements. So this is the improvement that you get by charging a different price for every number of cars that are on hire versus charging just one price. That's the blue line. The orange line is when you charge just 2 fares. You can see we're barely getting up to 1% here in terms of improvement. This is with n equals 4. We've done some tentative experiments with n being higher, and we see that percentage improvement does increase with n. But as I say, this is hot off the press, so there's not a lot more that I can add at this point. What's interesting then is that the simplest model is actually getting us quite a long way towards getting that good revenue. And I think that's one of my conclusions is, simple models do get you quite a long way there. That you add some complexity, it's getting you something which in this case is improving in the very low percentages. The other thing you can see from here is as the system gets busier, then the percentage improvement from having multiple prices goes up and then declines again. So what's happening at that very high values of lambda when the system's really busy is it actually doesn't really make much difference what those prices you charge are for the cases where you have in this n equals only 1 car on hire or 2 cars on hire or 3 cars on hire, because you almost never see those cases. So you spend most of your time in that very high all cars on hire state. So that's the reason why that declines as we get to very busy systems. Where the typical system would sit is probably somewhere around that peak. So that's in some ways the most interesting part for us. I'm going to just check the questions before. Varying the number of cars. Oh, I'm going to answer that one at the end, Stephen, because that is a good question. Is it possible to get more revenue? I will ask some of Zaffar's now. Is it possible to get more revenue from two fare comparing to state dependent case? No, that's not possible, because if you think about, if we have say 4 fares in our n equals 4 example, and we have 2 fares is the 2 fare example, you can think if just 2 fares is the best. I'm right, let me start again. That if you have 4 fares that you can set, and actually 2 fares is best, so 2 just different fares is best, you can always, as one of the options at the end of your optimization, set 2 of those 4 fares to be identical and the other 2 to be the other fare. And so the more fares you have, the better the revenue will be. So if you add the model where you have more options for different fares, will always give you higher revenue. It might be, and we saw that on the previous graph here, that as you get to very high traffic intensities, they actually end up basically returning the same thing. So if this lambda equals 200, for example, you're basically tending to a point where R0 equals R1 equals R2 equals R3. And so, yes, you will always see that. So the full state dependent will always give you greater than or equal to revenue than the 2 fare, which will be greater than or equal to the revenue from the single fare. Okay, so I promised a little bit on the demand responsive transport, and I also promised I'd be 40 to 45 minutes, so I will spend not too long on this. I only have a couple of slides. Demand responsive transport is another way of coping with those individual kind of unique journeys that can't be well served by mass transit systems. And in this case, pricing has a role to play in some ways in terms of how you might set the incentives. So in this case, if you're thinking of demand responsive transport or ride sharing, we want to encourage people to travel at times where it's efficient for the system that they travel. So we might give them more of an incentive to travel at a time when we know we've got a full minibus going in that, or almost full minibus going in that direction, very close to their house, for example. So you've got something there in terms of incentives. You also want to take account of the choices that the customers make. So incorporating some customer choice behavior into these models to allow us to understand the value of different route features to customers. So how much, for example, do they value the speed at which they get there? And does that vary with different times of the day? How much do they value maybe getting off slightly a little bit away from where they wanted to go to, but then they're closer to a bus stop or something else, and so they might pay a bit less, but which will help the routing, but will also not penalize them too much in terms of the time it takes them to get somewhere. So there's lots of things that that can then be used to feed into the pricing and the operations of these systems. But a lot of it is to do with demand management. And I've done some work on demand management for online grocery deliveries. And you see quite similar ideas there in terms of the models that you would use. So if you're pushing people towards the delivery slots, or equally in this case, the pickup and drop-off slots, that would help the system overall. What else is needed? So this is a little bit about what's going to happen in the next 3 years. So some behavioural modelling and forecasting, talking to people, running some surveys to see what's going on and being able to then forecast how people will react to different things they see in the system. Routing and scheduling algorithms and fleet size, yes, definitely. Also practical implementation and buy-in. So I think this is one of the big things, and what you see if you look at practical schemes that have been tried out there is how do we get people using this, which we're hoping some of the behavioural modelling will also help with. Just a quick advert for the Adroit team. So this is the DRT team that we're working with. I think I mentioned Julia and Chiara and Rim previously. We've also got 2 postdoctoral research assistants working with us, Rich Love, who is just finishing off her PhD at Loughborough at the moment, and Shobit, who is from the transportation science area. So Rich Love will be based at King's and Shobit at Leeds. So hopefully you will see them in the OR community again over the next few years. Just a few conclusions before I go to questions. I can see some of the questions have been popping up, and there's one I know I need to answer. The main point is serving that last mile of journeys is difficult, particularly outside of high density urban areas. And lots of people have banged their heads against this problem. And we're coming with our own set of potential solutions, but it is a difficult problem, and we're very well aware of that. However, the goal is quite a good one. So reducing car ownership will decrease our use of resources, and OR people are always out for efficiency. So this is something we should be kind of looking for. Less use of raw materials, less space used up because there are fewer cars around, no hunting for parking spaces, for example, and reduced energy usage from more efficient journeys. So this is obviously really important with all the quest for carbon neutrality. The other thing just on the methodology was that this relatively simple model gave us some useful insights into general results for the problem. And I think that's a nice thing to think about. It's not every problem that it works on, but it was quite nice on this one that we could come up with something quite simple, and it still gave us those general insights. And those simple models can also be used as either initial solutions or quick meta models or emulators, as the statisticians call them, for more complex simulations, for example. And finally, there's lots going on here in the UK and particularly in Europe. So there's lots of scope for interesting optimization and interesting new problems for OR people to solve, which is always quite exciting. I've included most of my references here. I realised 2 minutes before it started that one of them's gone off the bottom, but if there's any references you want, do get in touch. And then just a final thank you to the OR Society for the invite, EPSRC for funding the research, and Southampton for paying me for a while. So let's finish there with me talking, and I'm happy to answer any questions. I'll start with those that are there, but feel free to put some more in the chat if anything comes up. Okay, so I'll start with Stevens. Revenue optimization makes sense for an airline trying to fill airline seats and have a fixed capacity. In this case, isn't there more control over cost by varying the number of cars available? Have you looked at the interaction between price and capacity, and can these be optimized together? Good question. Yes. So I think I'd argue that if you're looking at day-to-day optimization of a fleet of cars in car share, then it is generally a fairly static capacity. So you haven't got that changing particularly over time. What we can look at is looking at fleet size and how that does affect the revenue that you get. At the moment, in the models that we're presented here, we're just looking straight at revenue, and we're not looking at cost, for example, in the car share model. And so you would have to bring in some idea of the cost of adding in an extra car to balance against the extra revenue that you would get from having that extra car. But that's definitely definitely something to think about. Where it also becomes more relevant is where the fleet is a little bit more dynamic. For example, you start with cars in central London, and then there's some going south and north and east and west, and actually, is it better for you as a company to have more cars in this particular area and move them over during the day, for example? So those kind of dynamic problems we haven't looked at, but would be a nice idea to look at that interaction. So yes, thank you, good question. Okay, anonymous attendee, slide 20, x-axis. Let me go and have a look at that. The x-axis along here is the price. So it's the price being charged. The y-axis is the revenue. Sorry, I probably didn't explain it very carefully. So what you can see, the maximum price we're allowing in this market is 1 and the minimum is 0. So what you can see is with the blue curve, for example, here, where lambda equals 10, you get a peak in your revenue around R equals 0.5, so in the middle of that range. Whereas with the very busy system, lambda equals 80, for example, the peak in the expected revenue is around, well, just under 0.8 that you would be charging. So what you can see is the more, the busier the system is, the more you should charge to get that maximum expected revenue. Hopefully that explains that. Okay, Nick. Have you thought about minimizing the risk to the customer of getting a car? The service needs to be robust. Yes, we have looked at that. So one of the things, I didn't present it here, but we do measure is the availability of cars. So what's the probability that a customer entering the system will find a car? As I said initially, we're assuming they disappear and so don't queue if there isn't a car available. And so it's quite important that we do make sure that there are cars there and the availability isn't too low. And in reality, I guess that's the business owner's decision to make, is where they want to be on that kind of curve between good availability and good revenue. And that probably comes back a little bit to Stephen's question on fleet size as well, is at what point obviously with a bigger fleet, you'll have better availability, but more costs. So yes, no, that's a good one. Yeah, very good question. Thank you. Right, and look in the chat as well. Have you thought about, no, I've seen that in the chat. Thank you. Would it be worth considering a Dutch auction model where price varies with arrival rate? So that is something that we look at in the time dependent case, where if we know that the arrival rate, for example, in rush hour is likely to be very high, if people are using cars to get into the office or wherever they're going, then we can charge more. And you can use this model for doing that, because you can say, well, actually, if we look at this slide, during the rush hour, maybe lambda's 30, so we'll charge something up here. During the rest of the day, lambda's very low, so our arrival rate is low, and so we can charge a lower price. So you can use this model to give you a guide as to what those prices should be. Where it's not so good is on that kind of transition point between rush hour and quiet time. But yes, that's a really good point. Okay, great. I think I have answered those 3 questions there. So are there any final questions before we finish off? Let me rush through to the end, so I've got my nice logos. Keep an eye on the questions. Have you considered a machine learning model as a long-term approach? That's a very good question that opens up a can of worms there, Eloy. I think one of the things I like about the OR modeling is that the model that you build has some reference to the structure of the problem. So you could throw this at a machine learning model and it will depend what machine learning model you use. So yes, there's definitely something in that, but whether you would be able to, by understanding the structure and putting some of that structure into the mathematical model that you build, in some ways speed up the optimization and improve the optimization over what a machine learning model could do. I'd like to think that you could. Where the machine learning model may come in is if you were looking at full state dependent pricing, when you get up to, say, n equals 100, so a fleet size of 100, and you want to charge a different price for each number of cars that are available, I suspect you probably wouldn't ever want to do that. But if you did and were really interested in looking at that, then actually setting up those transition matrices for the Markov chain model is a difficult problem in itself before you even start calculating the probability. So if you get to those very big problems, maybe then you would start, it might be that there's something there that machine learning could help with. But I don't think immediately that it would be my first step solution, if you see what I mean. But yeah, thank you. That's always a good one for debate. Great. Okay, I can't see any more questions. So, and we are coming up to 1 o'clock. Everyone's got to go back and do some work, I guess. Thanks again for coming, and thank you for the questions. Very, very useful, always useful for furthering the research. So thank you.